let's talk about polar coordinates, and in particular, Newton's second law in polar coordinates. Let me go ahead and start off with a situation that this is where you would use this. Imagine that I have a mass connected to a string, and that string can swing back and forth. So I could represent the motion of this with Cartesian coordinates. I could get an x position and a y position. I could get the gravitational force. I could get the tension. But the problem is that as this thing swings along this path, the tension changes both direction and magnitude. And in fact, you don't even know the magnitude of the tension force because it provides whatever force it needs to make sure that the path stays in this circle. So an easier way to model this is actually with polar coordinates. Because in polar coordinates, then we can, instead of representing x, the position of this is x and y, I can represent this with r and theta, and r is constant. So that's kind of nice. We only have one variable instead of two, and an impossible situation. So, but Newton's second law looks different in polar coordinates than it does in Cartesian coordinates. So let's just start off with Cartesian coordinates and show you why it's fine, and then we'll switch to polar coordinates. So in Cartesian coordinates, I can represent the position of an object as r equals x hat plus y hat. I'm going to do it in 2 dimensions. So this says that if I know how far in the x direction, I can call that, and I multiply it by the unit vector x hat, which is a unit vector in the direction of x, and then I multiply this y by y hat. You can see that if this is the vector r, which I'm using, there's 2 r's. There's the r vector and then the polar coordinate r. Just want to be clear. Then this x hat plus y hat is that. So that is one way to represent that. What's nice about this system is that if I want to, I could break Newton's second law into x and y directions. I could say F net x equals mass times acceleration in the x direction, and F net y equals mass times acceleration in the y direction. Now we'll write this as m x double dot m y double dot. So here x double dot is the second derivative of x with respect to time. And we use this double dot notation. Single dot is this first derivative. It just saves a lot of space. But the question is, well, what is x double dot? What is y double dot? Okay. Can we even do that? Can you even do that? What's ax? Is ax x double dot? Is that true? Okay, it is true. Let's show why. So if I have that as my position, I can find my velocity. So the velocity is dr dt. So if I take the derivative of this with respect to time, it's the derivative with respect to time, x hat plus y hat. So I have a product here. I have 2 things. I have x and x hat. So I have to take the derivative twice. So this is going to be the derivative of x, which is x dot, times x hat, plus x times the derivative of x hat with respect to t, plus y dot times y hat, plus the derivative plus y times the derivative of y hat with respect to time. Now, what's nice is that if I use Cartesian coordinates here, x hat and y hat, and then over here I have x hat, y hat, the Cartesian coordinates don't change. They don't depend on the location. So the derivative of x hat with respect to time is 0, and that's 0. So this gives me x dot x hat plus y dot y hat. If I take the derivative again, I get the acceleration is x double dot x hat plus y double dot y hat. So I mean, we take that for granted, but it is important, right? And now I can break this into an x double dot is the force in the x direction, y double dot is the force in the y direction. I mean, it's a huge deal. Okay. So let's do the same thing with polar coordinates. Now, a lot of times if you're doing a pendulum, you'd measure the angle from here, but it doesn't matter. A lot of times you measure the angle. It doesn't matter as long as you're consistent. Just like I could call this positive y, it just doesn't matter. So let's go back over to this situation. So here's this is the x direction. This is the y direction. Here's some particle. It has a vector position r, but I represent that with a polar coordinate r and theta. And I know the relationship between these. I know that well, I know x is this value, x, and this value is y. So x equals r cosine theta, y equals r sine theta. Now, if as I move, let me switch back over to here. What makes this difficult is, no, I'll do it right here. What makes this difficult is I can represent the vector r as in terms of r hat and theta hat. So r hat shows the direction of r, so that'd be this way. And theta hat shows the direction of increasing theta, which is this way. If I increase theta, it goes that way, theta hat. But you'll notice that if I move over here, then now r hat is this way, and theta hat is that way. So r hat and theta hat are not constant. They change as the thing moves around. That makes it very complicated. But I can still represent the position of this as a vector in polar coordinates r hat. Right? So it says go a distance r in the direction of r. That's what that says. That's my position vector. Let's take the derivative of that. So I need the second derivative, right, to get the acceleration. So dr dt is going to be equal to the derivative of this. Let's just write it out. d dt r hat. So again, I'm going to take the derivative of r. So it's going to be r dot r hat plus r times the derivative of r hat with respect to t. But what's the derivative of r hat with respect to t? It's not so obvious, right? And it's not obvious at all. So what we need to do is to get r hat in terms of x hat and y hat. If I can do that, then I can take the derivative since I know x hat and y hat don't change. So I can write this vector r as x hat plus y hat. No, that's not a dot. And I can use these values, these expressions for r, x, and y to get in terms of r and theta. So it's going to be r cosine theta x hat plus r sine theta y hat. But what about r hat? I want to take the derivative of, if I took the derivative of r, I could get that, but I want to take the derivative of r hat. So I need to get r hat in terms of x hat and y hat. Now, a lot of times books will just say, "Oh, it's just obvious, can't you see?" But let's not just see. Let's do r hat. If I have any vector a, then a hat is equal to the vector a divided by the magnitude of the vector a. So it's normalized. And the same thing's true for r hat. It's going to be the direction that r changes, but it has to be normalized. So I can say r hat is going to be the partial of r with respect to r, and again, that's the vector position r, and that's my variable r, divided by the magnitude of the partial of r with respect to r. So let's do that. I'm going to use this as my vector for r, so I can take the derivative, the partial. So the partial of r with respect to r is going to be the partial of r with respect to r of r cosine theta x hat plus r sine theta y hat. So if I do that, I'm treating, there's a partial derivative. So I'm treating everything that's not an r as a constant. So right here, the only thing that's not constant are these r's. So if I take the partial of this term with respect to r, I just get 1 times cosine theta x hat. So I get cosine theta x hat. And then the partial of this with respect to r is just going to be plus sine theta y hat. Now I need to find the magnitude of this vector. So the magnitude of the partial with respect to r is going to be equal to, if I have a vector in Cartesian coordinates, the magnitude is this squared plus that squared, and then take the square root. So it's going to be the square root of this squared, cosine squared theta, plus that squared, sine squared theta. And sine squared plus cosine squared is 1, so this is just 1. So that gives the following. R hat is going to be cosine theta x hat plus sine theta y hat. Now we're going to use this. I'm going to go ahead and I'm going to have my little sheet of stuff that we're going to reuse. I'm going to put that here. I'm going to put r equals r cosine theta x hat plus r sine theta y hat. R hat is cosine theta x hat plus sine theta y hat. Okay. So now I have r hat. I can take the derivative of r hat. So let's do that. The derivative of r hat with respect to t is going to be the derivative, not the partial, with respect to t of this, which is cosine theta x hat plus sine. You know what? I'm going to do that. Let's do first the derivative. Let's find theta hat. I have r hat. I know ahead of time. I need theta hat. So let's say this. I'm going to put up here. R equals r cosine theta x hat plus r sine theta y hat. And so theta hat is going to be equal to the partial of r with respect to theta divided by the magnitude of the partial of r with respect to theta. So let's take the partial of r with respect to theta. The partial with respect to theta of r is going to be the partial with respect to theta of r cosine theta x hat plus r sine theta y hat. So if I take the partial of that, again, the r is a constant, so nothing happens to it. I have to take the partial of cosine with respect to theta is negative sine theta. And then it's a partial, so I don't have to do anything with the theta. X hat's a constant, so I get minus r sine theta x hat. Now if I go over here, the partial of this with respect to theta is just going to be plus r cosine theta y hat. Now I need to find the magnitude. So the magnitude of the partial of r with respect to theta is going to be equal to the square root of the x component squared, which is r squared sine squared theta, right? The negative sign goes away because I squared it, plus r squared cosine squared theta. And then I can factor out an r squared, and I get r squared times the square root of sine squared theta plus cosine squared theta. And so that's just, that's r. I factored it out. So it's just r. So now I can go ahead and calculate theta hat. It's going to be this partial of r with respect to theta divided by r. So I get negative sine theta x hat plus cosine theta y hat. So let's put that over here. Theta hat is negative sine theta x hat plus cosine theta y hat. And so you'll see this in a lot of books where they just say, okay, look, if this is theta, then this is theta. So you get this x component's negative sine theta, the y component's cosine theta. I get that. That's good. But in their cases later, if you do this in spherical coordinates, you can't see what that is. You got to do it. Okay, I wrote that over there. So now I can take the partial of r hat with respect to t, the derivative. So d r hat dt is going to be the derivative with respect to time of cosine theta x hat plus sine theta y hat. So if I take the derivative, I have to take the derivative of cosine theta is negative sine theta. So I get negative sine theta. But I'm taking the derivative with respect to t, so I actually have to take the derivative of theta too. So I get theta dot. That's the derivative of theta with respect to t. And then I have x hat has just there because it's a constant. Now I need to take the derivative of sine theta. I get cosine theta times theta dot y hat. Now let's factor out the theta dot, and I get theta dot times negative sine theta x hat plus cosine theta y hat. And by golly gee, look at that. That. So this is equal to theta dot theta hat. So let's put those two derivatives up here. Oh, that's only one. So I'm going to put the derivative dr hat dt is theta dot theta hat. Okay, so now we can go back to our derivative of position. So r equals r hat dr dt, we already said this, is r dot r hat plus r dr hat dt. I did say that, right? I think I did. If I didn't, hello, that's it. Okay, so now I know this is going to be equal to r dot r hat plus r theta dot theta hat, because I put in my value for that. And that's the derivative. That's r. This is going to be my velocity in polar coordinates. So let's write that over here. V equals r, what did I just say? R dot r hat plus r theta dot theta hat. And so we can make sense of this too, right? This says the velocity meters per second towards or away from the origin. And this is r theta dot. This is like r omega. This is the tangential velocity. This is the velocity in the direction of a circle. And you can have both of them at the same time. Pretty cool. Okay. Now we need to get the acceleration. The acceleration is equal to the derivative of the velocity with respect to time. So it's going to be d dt of this r dot r hat plus r theta dot theta hat. Now, and remember, that's a theta hat, r hat. Remember, all of these terms can change with time. So we're going to need to use the product rule. So let's do this one first. The derivative of r dot is going to be r double dot r hat. And then I take the derivative of r hat. I'm going to write it out. Plus r dot dr hat dt. Plus, now here I'm going to get three terms because I have a product of three things. So I'm going to take the derivative of this first one. It's going to be r dot theta hat. Plus, now I've taken the derivative of theta dot, r theta double dot theta hat. Now I need to take the derivative of theta dot. Plus r theta dot theta hat. Okay, so I already have an expression for the derivative of r hat with respect to t. Oh wait, d theta hat dt. But I don't have d theta hat dt, so let's do that. So if you recall from right here, I have an expression for theta hat. So let's take the derivative of that. D theta hat dt equals d dt of negative sine theta x hat plus cosine theta y hat. So if I take the derivative of that, I take the derivative of sine theta with respect to time, I'm going to get negative cosine theta, and then I have to take the derivative of theta, so I get times theta dot, I'll put that in parentheses just so we're clear, and then I have x hat, and then I have the derivative of cosine theta is negative sine theta, and then I have to take the derivative of theta, theta dot, y hat. So if I write that out, I'm going to factor out the theta dot. I'm going to factor out the negative theta dot. Negative theta dot cosine theta x hat plus sine theta y hat. And look at this. R hat. So I get negative r theta dot. No, wait, negative theta dot. Where did I put the r there? Negative theta dot r hat. So let's put that up here. D theta hat dt is, what did I just say? Negative theta dot r hat. Negative theta dot r hat. So now back up here, I can rewrite my acceleration. A is going to be r dot double dot r hat plus r dot times the derivative of r with respect to t, which is theta dot theta hat. So I get theta dot theta hat plus r dot theta hat plus r theta double dot theta hat plus r theta dot derivative of theta with respect to t, which is negative theta dot r hat. So I'm going to change this to negative theta dot r hat. Now let's group together our terms. So I want all my r hats. So this is going to be equal to all the things that have an r hat. So here's an r double dot. What other r hats do I have? Right there. Minus r theta dot times theta dot squared. R hat. Now let's group together my theta hat terms. So here I have r dot theta hat, r dot theta hat. So that's going to be 2 r dot theta dot. And then I have this other term plus r theta double dot theta hat. And so that's my acceleration in polar coordinates. Let's put it up here just to be complete. A equals r double dot, what did I just say? Minus r theta dot squared, right? Yep. R hat plus 2 r dot theta dot plus r theta double dot theta hat. So if I want to do Newton's second law in polar coordinates, I can say this. I can say F net r is equal to this mass times r double dot minus r theta dot squared. F net theta is going to be equal to mass times 2 r dot theta dot plus r theta double dot. And there you go, Newton's second law in polar coordinates. Now, let's just go back to that pendulum for a second, right? Because in the pendulum, r is equal to L, right? Some constant length. So if that's the case, what's the derivative of that with respect to time? Well, it's going to be 0. And what's the second derivative with respect to time? It's going to be 0. So that's going to simplify this, right? So now I'm going to get m L theta dot squared, and then down here I'm going to get m L theta double dot. That term's going to go away. That term's going to go away. So it does make it simpler. Now, but we can also make some understanding of this acceleration up here for the different components. So this is the acceleration towards or away from the origin in meters per second squared. This is meters times radians per second squared. If you say theta dot is equal to omega, the angular velocity, then this is going to be r omega squared, which is equal to v squared over r, which is ac. That's the centripetal acceleration, which points towards the center of the circle. That's why this is negative. Okay, so you get centripetal acceleration from here. It's in the negative r hat direction. So that's acceleration towards or away. That's the centripetal acceleration. Over here, this term, if I say theta double dot is the rate of change of the angle as alpha, then this is going to be equal to r alpha. And that's the at. That's the acceleration in the direction of the circle. That's a tangential acceleration. So that's what this is. And this term is the Coriolis force. If you're moving both, have a velocity towards or away from the origin and it's moving sideways, you'll get an extra component. And that's the Coriolis force. So there you go. That's the velocity and acceleration in polar coordinates. Can you do the same thing for spherical coordinates? Yes, you can. Will I do it? I hope so, but I'll tell you right now, I tried to do it once before and I got bogged down. It gets a lot more messy than this. 1, you have 3 dimensions. 2, you got a lot more derivatives and stuff. I'll try to do it at some point. If I do it, I'll be very impressed with myself, but this one's not too bad. So, okay, there you go. Hopefully that helps.